All right. Cool. So I'm going to talk a little bit about neural fields and visual computing and beyond. It's
Idea. Turn off the.
I think that's over here. So I'm gonna. Sorry. All right, I have too many slides here, so we're not going to get through all of them. I'm hoping to get through like part 4 in the paper, or section 4 in the paper. But we will see. I think I will cut it off at 7:30. Does that sound good?
Yep, that sounds good.
Okay. Does anyone else have a hard cutoff? Oh, hi, Andrew.
Hi, Andrew.
Hey there.
Hey, Andrew.
It's a weather for Zoom meeting.
Weather for a Zoom meeting. Yes, that's right. My ankles are wet. I'm sad about it. Okay, so with this, I like the structure of the paper, so I'm very closely following that. But really what my hope is for folks who have some experience in this area, Garrett, and I've got a bit of experience in a different aspect of this that isn't there. We can talk a little bit about how our experience kind of coincides with the paper, some of the personal experiences with training these networks. There was a whole section on sort of implementational tricks, like this, dealing with the spectral bias in neural networks. So, how has it worked for you? And trying to make it a little bit more personal, because I think what this paper was, or what this paper is a really nice summary of this kind of emerging field of treating neural networks not as surrogate functions that are supposed to generalize over a large problem domain, but rather as a method of compressing some kind of physical field into a continuous functional representation. And it just, that little shift in the perspective of what is a neural network supposed to do and how are we training it, means that we can, it kind of opens the door to different classes of problems in a really cool way. So, without further ado, I guess before we get started, did anyone have any like pressing comments, questions, concerns, complaints they wanted to make about the paper? Initial perspectives? Actually, quick show of hands. Who read the paper?
Yeah.
Good. You opened link to the paper. You confirm paper exists. Cool. Okay. Yay, Garrett. All right. Then for those of you who didn't look at it in more detail, basically what this is a review or kind of a aggregation of 250 recent papers in the area of what they're calling neural fields, which I'll define in a moment. But they are grabbing all of these papers, taking a look at some of the commonalities. They have a part 1 and a part 2. Part 1 focuses on techniques, like what are people using, or how are people representing these functions? Why are they representing them the way that they're representing them? What are the pros and cons? What are some of the practical considerations of training and using these things? And then part 2 is applications, which is, okay, so we have this neural network field thingy. What are we going to do with it? And I think we will probably not get to part 2, but we'll see. It was put together by a fairly diverse group from several different universities. Actually, the lead author is an undergraduate, which I think is really interesting. I was a little skeptical, but then I watched his YouTube talk on this, and he is extremely put together. I think he's technically a PhD student at Caltech now, but it is a group from, I think there was Brown, there was MIT, there were a couple of, I think NVIDIA's involved, a couple different organizations and some big names in some of the folks who have produced some of the, I guess, groundbreaking papers in this area. So it's just kind of a goal. The goal is to sort of wrangle the field. Speaking of fields, what is a field? How do you all define fields? This is interactive, so someone has to say.
Value spread over a 3D volume.
Yes. Awesome. That's basically what they said in the paper. a quantity defined for all spatial and or temporal coordinates. There can be a temporal aspect as well. And if you can project it onto a spatial or temporal coordinate system, that works too. So here are some examples of physical fields in physics, not necessarily neural. On the left, we've got a pressure field from a piston. Then we've got a vorticity field from a basically vortex jetting as air flows across a plate or airfoil. I'm not quite sure what's happening downstream there. Then we've got the surface temperature of the Earth. And finally, we have something slightly different, which is a sign distance field, which is a representation of a 3D volume. So all kinds of different fields. They are really, really important, and maybe important is the wrong word. They are absolutely indispensable in physical simulation. So it is a very important part of trying to model the world around us or figure out what's going to happen. So what are neural fields? Oh, sorry. And here it is a table from the paper, just kind of talking about some different fields. Oh, right. So some questions here to consider are, what forms can these fields take? You know, in real life, everything is this. I guess if you look at life with the right level of abstraction, everything is a continuous quantity. When you get a little bit deeper, then maybe it gets discrete, but I'm not that kind of physicist. So everything is continuous. But then we start recording things with sensors and then translating them to digital formats. Things get discretized. Instead of dealing with this continuous, voltage, for example, we're going to be dealing with zeros and ones. So there are different ways of considering these fields. You can have a closed form analytic solution, for example, where you have the exact differential equations. You can have a bunch of recordings that you step into a lookup table, and like a pure data-driven, table-driven approach. You can have a model that you've developed, a phenomenological model, based on your lookup table. You say, okay, this is more or less what's happening. We're doing a polynomial fit or whatever. Or you can have a neural network, which is what we're going to get into next. There are different ways of representing these fields. One big decision you have to make when you're trying to figure out how to represent these fields to use them in something, whether it's a fluid dynamics simulation or if it's a rendering problem, trying to decide how are you going to represent your 3D geometry, is a question of discrete versus continuous. And this might just seem like an efficiency question, but there are major implications to like the quality of your simulation, as well as the computation time. When you discretize things, you introduce error. One very common consideration when you're doing discretization is aliasing effects, for example. I'm looking at Garrett because I'm sure he is familiar with this, where it becomes ambiguous what signal you're actually trying to represent based on your sampling frequency. So you have to make decisions about, okay, how frequently am I going to sample in order to discretize something? And that might change over the course of your signal. With continuous representations, that could be great, but it could be a very, very complicated function. Something very nonlinear or something not, totally obvious. So there are trade-offs with these two representations, and very often, I guess in classic numerical modeling, we take discrete representations or continuous representations based on discrete data. So with that said, what are neural fields? A neural field is just a field that we are parameterizing either wholly or in part by a neural network. If you've read related literature, you might see this as implicit neural representations, coordinate-based neural networks. Basically, it is a neural network that takes a position, X, Y, Z, or I don't know, R theta, or whatever it is. Basically a 2 to 3D position usually, sometimes with time, and you output a value, a non-spatial value. So that could be, a chemical state. It could be a scalar value like temperature. It can't be like a 3D patch. You can't have any spatial aspect here. That's something that's not a neural field. But basically it just, you're replacing that lookup table with, this neural network. That's a compressed, continuous, differentiable, functional representation. So, I guess, quick, quiz for interest or understanding. Why do you think a neural network is an advantage over something like the lookup table?
You repeat the question, Lee?
Oh, sure. Why do you think a neural network is, or what do you think you could do differently with a neural network than you could do with a lookup table? Why might you want to represent a field as a neural network?
You
So
can be
I
quite
think more
clever.
flexible. I think I'm more flexible with the field, because with the lookup table you kind of restrict by the functions that show your functions, right? But the field you can got and output into any function you want, and I think that really broad,
Yeah,
really broader, right? You're not restricted to any like function choice. And I think for certain problems like the field approximation, you capture the global approximation and the local approximations.
yep. Flexibility is a huge point here. And yeah,
That was but yeah, like you can draw things that weren't in your original data set, like you don't.
exactly.
Like, yeah, you can.
Interpolation is a huge point here, yes. And I think that goes back, well, actually, I guess that's a little bit different flexibility. Yeah, you can work on different domains than you expected, you can work on different scales than you expected, and you can interpolate between sparse data points and, generate novel views, for example. Totally random example that has nothing to do with one of the biggest papers in the area. So neural network, and beyond that, neural networks are compressive, or are very compact. Because of those nonlinearities, there are a lot of universal approximation functions. You can do Fourier expansions, you can do polynomial expansions, you can, do JPEGs, I don't know. But neural networks are, and not only are they continuous, with those interpolated values, not only can you put them on different domains or define them such that they are independent of variables that change, that we'll see later. That's a really cool idea in this whole thing. But also they can be quite small for what they're representing. There's a paper called Acorn, which I'll show a little bit more of later, that actually I believe has reduces the number of quote unquote parameters of a high definition image. It reduces it by a factor of 80. Which I believe gets better than the JPEG compression that they were comparing against. It was a fairly early on approach, so it didn't have a lot of it. Like, I don't believe it used positional encoding, for example. But they can be quite efficient. So yes, this is pretty much what we hit on. Neural fields are compact. They're also regularized. When you're training a neural network, you can regularize based on what you're interested in. So exact, like photometric loss is important if you're trying to compress an image, for example. But if you want to learn a geometry, maybe you want it to be smooth. Or if you're trying to learn the sine distance function, then you need to have an econial term to make it a bit econial term. I'm never sure how to pronounce that. Any actual physicists can feel free to correct me. To make sure that it's actually a valid function. Or you can make sure that it obeys your governing equations. You have a lot of flexibility in the training here when you use stochastic gradient descent. And like Garrett mentioned, neural fields are domain agnostic. They're really flexible. You can actually separate the parts of your domain that change from your neural parameters and learn only the parts that you need to. And that makes it really, you'll see some examples of this later also. There's a really great paper called Nerf in the Wild that takes, random pictures from anybody from whatever angle using whatever camera and at whatever time of day or whatever weather, and really separates out the 3D geometry and random stuff that people add in a really, I guess, satisfying and successful way. But why do we even care about this? Here, actually, I want to ask what people's experience is in this area. Has anybody here actually worked with neural fields in their work or in their hobbies, or is this just kind of a new field for you? Start with you.
Yep, I have actually, as of like last week or maybe the week before last, I have actually used them in my actual paid job for real, literally for a hackathon, but.
Can you tell us what you were reconstructing?
So we actually put together quite a, like, it was a 3-day hackathon and we did it shockingly easy to do this. We actually like used making ran an image to image like model on the, so we rendered artificial images, training images for the nerve, using just a regular renderer, and then ran those images through image to image machine learning model to actually change them based on like natural language prompts. So you could say like, make this cheese, and it would be cheese. And it just worked. It was like shockingly like powerful actually. And like even though like obviously the image to image function didn't do a particularly good job of getting like it didn't make it particularly consistent between. It didn't change each image in the same way, so your signal would just end up with a mess. But it actually worked pretty well. Like you ran it through Nerf, and it did a pretty good job of saying, hey, here's this 3D model, let's make it cheese, let's make it futuristic.
You're able to synthesize like totally random imagined?
Yep.
Wow.
It worked very well.
Neat. Anyone else? I can see. Andrew said, I don't have experience with neural fields, but there's an iOS app called Luma AI that makes nerves available for anyone to generate their own, and has experience in 3D reconstruction, which uses a different process to reconstruct. Cool. So you have felt the pain, right? Awesome. I guess for me personally, I don't work in graphics, but in acoustics right now, I am working with some of my lab mates on basically trying to parameterize certain room parameters of the field and do some design optimization on them. So can we, for this particular project, it's sort of a quick and dirty thing, but can we, using an acoustic a room impulse response code, can we actually design rooms with the acoustic properties like tinniness or like speech clarity that we want? And at work, we're trying to get into similar to that, but instead of room design, designing acoustic metamaterials. So basically these highly anisotropic material structures that you build around your sensors in order to like passively compute, bend the wave in such a way that it performs some kind of computation before you actually hit your sensor. So really cool sci-fi problems. I'm enjoying it, and hopefully it'll work. But in general, anyone, does anyone else have experience that they'd like to talk about? In general, why do we care about this field? This, I mean, these ideas, you know, parameterizing fields, trying to come up with these phenomenological models, certainly differentiable solvers, they've been around for a while. I actually have a problem at work where I mentioned differentiable physics, and the mathematicians laugh at me. They're like, our codes have been differentiable for ages. All these people putting new names on old things. I've learned not to say those words because it means that they disappoint. Right now, I think we're at a confluence of events where the algorithms for machine learning, particularly neural network training, are developing super fast. We've made huge algorithmic advances here. At the same time, we've advanced our hardware accelerators. These GPUs are able to churn out so many matrix multiplications, which is necessary for the stochastic gradient descent. At the same time as we are getting better at, you know, data storage and transfer. Basically, a bunch of different things are evolving, largely because of the popularity of machine learning, that all of a sudden we can use neural fields and these differentiable solvers to solve like ridiculously, hilariously ill-posed inverse problems. High dimensional data compression is a forward problem. It's trying to come up with a better way to, you know, squish a video together. But we can, directly optimize meshes, for example, based on, a whole bunch of kind of soft constraints, different priorities. We can solve super ill-posed imagery construction problems, like given a handful of images of something else, apparently. Some other random rendered scene. You can reconstruct a totally different scene. According to the hackathon. Which, 10 years ago, that would have been unheard of, right?
Yeah, totally. It's like kind of magic. It's like how well it works.
Yeah, there is a professor here who, shoots lasers through keyholes and can reconstruct what's happening in the room. And also this gradient-based design optimization, being able to actually optimize engineering design by directly accumulating gradients through a solver. It means you can optimize on real data. And do so much faster than you could before with like a simulated annealing type approach. And I guess if you talk to me offline, I'm very concerned about things like climate change and, the future of the world and all of that. And from what I've been reading, we need huge technological advances in like carbon capture and efficiency design, et cetera, to, not die. And things like this gradient-based design optimization. It's such a powerful tool, and I think it'll enable a lot of that. And then finally, universal differential equations. It's just a really cool philosophy of actually making the data and the physics work together to come up with systems we trust. So I think this is a super cool field, and hopefully you all do too. But how do I? All right. Before I get into the details, anyone have anything they'd like to add or throw in there? Particularly, actually, a discussion question. Is there anything about the paper that you were confused about, or that I guess related to your particular interests that I should be sure to touch on? Bless you. Cool. Yay, Zoom meetings. Okay, so this is a if you want to follow along in the paper, this was a figure in the paper that described a typical feed-forward neural field algorithm. So it uses a neural field, and did I miss something? I touch on the MLP details. Sounds good. The networks in these tend to be actually quite simple, which is cool. But there are also, in addition to the MLP, there are some tricks that they talk about with how to train these things that I think are really, really useful. And I think I'm about to put positional encodings on all of my neural networks because they seem to just make everything better. Yeah, so this is a example of a feed-forward neural network algorithm. That there are two actually. The one on the top is NERF, and the one on the bottom actually I'm not familiar with, but I believe they are turning I think they're just changing depth and normal images into signed distance fields. So changing the internal representation of the geometry, but I'm not sure. If you're interested, you can check out this paper. But in the first part, we are coming up with our neural network representation. The input is coordinates and the output is something here. So following the top path, you all were at the NERF talk. So I'm sure you all remember in great detail that the output of the NERF network is C, which is the emitted radiance at a given point, as well as rho, which is the density at a given point in 3D geometry. And then when you do this section 4, volumetric rendering, You do path tracing, or you do tracing, not path tracing, sorry. You shoot a ray into your 3D volume and you basically accumulate those densities and those emitted radiances and get your pixel color as the output. And then when you get all your pixel colors for all these little points on your image plane, you get this RGB image. So that's an example of how you would use in a forward way a neural field. You have this neural network that gives out those radiance and density functions, and from there you get what you want. And they describe this as going from what they call the sensor domain, or the reconstruction domain, this 3D volume, to the sensor domain, which is an image. And this just shows how they're breaking down the sections. And why isn't, sorry, my arrow wasn't working. So here's some more detail on those sections. Section 2 talks about prior learning and conditioning. Section 3 talks about hybrid representations, and we're going to kind of skip through that a little bit because I don't find it quite as interesting. Feel free to stop me if you want to talk about it. It's basically hybrid continuous discrete presentations for efficiency. Section 4 talks about forward maps. I think that's very interesting because when you start talking about forward maps, you can start talking about inverse problems. Section 5 is super interesting. It talks about, and actually we should make sure to get to this because Andre's interested in this, the network architecture. So, you know, again, typically these things use pretty simple MLPs. Sometimes it gets a little bit clever in how they combine multiple MLPs. But what gets really interesting is some of the observations about how these MLPs train, such as spectral bias. Some of the additional requirements on the MLPs, such as having to have higher order derivatives. And some of the more, I guess, physics-based concerns about what are you actually training this MLP on, so sampling, for example. Very often you'll have two-stage networks. And then manipulating neural fields is like, what do you do with this? Constraints and regularization, which I probably won't touch on too much. So section 2, prior learning and conditioning. Before we get into this, who here feels like they understand what conditioning means? I had trouble with this the first time I read the paper. Hello.
So, sorry. So when I hear the word prior learning and conditioning, I talk of Bayesian learning, like Bayesian statistics and prior statistics. That's how I think about prior learning. But yeah, what do you take on it?
Okay, I think I lost part of that. But I think Andrew wants, or yeah, I think I'm going to go through this anyway. But you're probably right. I assume that. Conditioning was kind of a new idea. Actually, first, I don't know that we've met.
Hello,
Hi.
my name is Matthew Fowle. I'm a graduated 05.
Oh, nice.
Yep, I'm from DC.
Cool, cool.
And Gareth, the organizer.
Awesome. Thank you so much.
Lee, the other organizer, and Forsyth with the PowerPoint.
Nice. And hello, online world. Greetings.
Why don't we do around?
Hello.
Well, now we have people to introduce, we should.
Out of curiosity, how did you find out about the group?
I just like pretty wide net of meetup, and I definitely knew about Papers We Love as a concept from way back, and awesome idea, and love the philosophy. So don't have like vaguely aware of the machine learning world, but like just more for the Papers We Love in general, like spirit, and getting meetups going again. So
Yeah.
very excited to be here again.
There was good weather for it.
Yeah.
Good night for a Zoom meeting. You know, and you are being recorded, so anyway.
Yes, thank you for letting me know.
Oh, there is a little thingy in the middle, here in the corner. Oh, do we want to do online introductions or is that going to be too?
But, if anyone particularly wants to do, I think we should possibly just put on, unless we want to do an online introduction round. Yeah, I think just push on. You can introduce yourself afterwards remotely. Yeah. Like, so,
Push on.
Yeah.
All right, thank you, Micah, someone needed to make a decision. Cool, so just to let you know, I think I made my PowerPoint too long, so I figure we'll just cut off at 7:30 and we will end where we are. Hopefully it'll be at the end of part 1, which is focused on techniques in neural fields. And this is the first technique, which is really fundamental in the whole thing. And I've alluded to it before, conditioning. Conditioning is a weird word because I think of conditioning and I think of like linear algebra, matrix conditioning, stuff like that. And that is not what they're talking about. I think they're talking about it from more of a probability sense, like, conditional distributions and all of that. But they introduced the term conditional neural field, and that is a neural field that is conditional on some kind of other information that is represented by a latent vector Z. So basically the idea is that you have a bunch of stuff that you don't know. You have this field, but really, like Garrett mentioned, you don't, but one of the benefits of a neural representation is that you don't necessarily need to work on a grid, or you don't need to work on a uniform mesh, or whatever your underlying representation is. You don't even need to, let's say you're trying to find solve the heat equation on a car. What if you want to solve the heat equation on a different car? Does that mean that you need to come up with a whole new neural network that works on that kind of domain? This idea of conditional neural fields kind of frees you from that. It lets you separate into 2 parts the shared parameters that you're learning that are relevant to everything in your domain, and then your instance specific parameters that live in a latent vector Z. This was a little confusing, so I actually grabbed my favorite paper that implements this, I think, really well. Who here has heard of NERF in the wild? Have you?
I don't think so. I can see if it's in my library anywhere.
No worries. It's a really cool paper. I recommend it. Have you heard of it?
The name is familiar, possibly just from being mentioned in previous meetups.
So NERF is a really cool thing that basically you take all these pictures from different angles of this 3D scene, and you're able to reconstruct the 3D scene. You get this volume representation, and you're able to interpolate between those points and, spin the camera around when you only had 100 images originally or something like that. Which is great. That's a really cool thing. But what if you want to go to some kind of, famous monument? You want to get a 3D rendering of an old object that no longer exists, that was destroyed. You want to take advantage of crowdsourced pictures that are just available on the internet and train these 3D models. The problem is that doesn't work super well with NERF. NERF is actually fairly limited in its application because it assumes that your input observations are very controlled. You need to know your camera intrinsics, and not just that, but they really should be the same, I believe. You need to have the same lighting situation for all of your input images. It really wants you to have almost exactly the same scene each time. What NERF in the wild does is it says, okay, let's say we have a learned appearance embedding, which is all the stuff unique to a picture. We're just going to pull that out, use a neural network to learn that, and separate it from our neural network, and separate it from the rest of what we're doing. And then we're going to let our neural field network just learn the 3D geometry and radiance field. And that means that you can take all these images from the internet and fly around, national monuments, things like that. to demonstrate this, I'm going to play the video. This little video in the corner shows varying the appearance embedding on the same image. So you can see what the appearance embedding here is representing. I guess they're also spinning it a little bit. I think here they're just kind of interpolating in one direction from, I believe it was Day to Night. If you Google Nerf in the Wild, they have a project website that's fantastic. It's got tons of videos and tons of explanation. But this is an example of a latent vector Z that embeds the picture specific information. Basically, you're taking out the stuff that you can't control, dumping that into like an encoder decoder network or something, and making then your actual neural field much more powerful. So here they discuss two different ways of doing this. First is an encoder approach where you have this kind of jointly trained encoder, and second is separately learned latent codes. And they're the same idea. There are different ways to implement this, and you can see that in different papers, but the core idea is separate out the things you can't control and dump them somewhere else. And that gives you a ton of flexibility. Similarly, like Garrett mentioned as well, this can be done on a local or global scale. Global is great because it's compact. You have one latent code for your entire image, like it's night, for example, or these are your camera intrinsics. And it means you're not passing a lot of data around. With local though, basically the idea is you have some kind of discrete data structure, a bounding volume hierarchy or something where you have a bunch of like cubes that enclose different areas. And you vary your discrete data structure, you find the appropriate box, you pull the neural network out of that box, and that's your encoding. So it lets you give a little bit of locality to your system. And that's great if you have different, I don't know. If the atmosphere is foggy and it's different amounts of foggy in different places, for example, like you've got weather. You can also kind of combine this. So some parts of your latent code can be global, some parts can be local. It can be local in different ways, representing different aspects of your system. There's a lot of flexibility. And then finally, the last part in this section was talking about, okay, so you've got this latent vector that is encompassing all the stuff that we don't want to deal with. How do you then turn it into a neural network? And they've got a couple examples here, but the core idea is that you have some function by psi rather, that you dump your latent vector in, and then you get out neural network parameters. The way I've seen this done most often, the way they do it in Nerf in the Wild is with concatenation. You concatenate your vector Z with your neural network parameters, and boom, you have your actual neural network parameters. There are also hyper networks where basically you put Z into a neural network and whatever comes out is your neural network parameters. And then there are feature-wise transforms, and I'm sure you can come up with other ways to do this too, but there are pros and cons to each. But this is a really cool idea because it just gives you I guess it brings you from the laboratory setting to being able to work on real world kind of crowdsourced data that you don't have a ton of control over. And it just makes it such a useful technique, especially if you're trying to go from real world data to these neural models in, for example, going from experimental physics to some kind of models that you can do a simulation, or that you can run simulations on for places where we don't actually have detailed models of the physics. So it's very exciting. This paper does not mention where, the question was, does the paper mention where the latent code is concatenated? I don't believe this paper goes into detail on that. I believe though that the Nerf in the Wild paper does. But I believe that it's basic, if I remember right, it's concatenated to the input. So I guess if we go back to that Nerf in the Wild MLP diagram, so you've got your input to your neural field MLP is your 3D position. and viewing direction. Was that? Oh, right, so it looks like in this one, you have your 3D position, put it into the MLP and you get out density. And the density doesn't depend on your viewing direction. It doesn't depend on the appearance embedding. It only depends on your 3D position. But then when you get to the second green MLP, it puts out the output of, it takes in the output of the first MLP, the viewing direction, because the color might change depending on what angle you're seeing at. And then the appearance embeddings, and all that is concatenated together and shoved through the second MLP. So the second MLP has quite a few inputs. And then they also have transient embeddings, which is for like random people wandering around in the scene, but you don't actually want them in your 3D model. This probably varies a lot paper to paper, so whatever makes sense for your situation. But this seemed to work quite well for them. There was also a section in the paper about gradient-based meta learning, and the core idea here is that instead of training a neural network, you're trying to train a class of neural networks. Instead of trying to train one neural field, you're trying to train a class of neural fields. So, say for example, you want to, I don't know, do some kind of video. I think Dr. Zwicker here at UMB had a paper recently where they were using NERF to do 3D rendering of a very large theme where you were kind of flying through different areas. And basically they just retrain the neural network every, n steps, or fine tune the neural network every n steps. Instead, you could do a meta learning approach where you initialize the neural network for the kinds of rooms that it would need to see, doing the kinds of tasks that it would need to do. And ideally then with one or two samples, it would get to where it needs to be. But I didn't find that quite as interesting, so I didn't have more details. Any questions, comments, concerns on prior learning? Cool, that's how I know everyone's paying attention. I think this part's really cool because it sort of frees it from the bounds of the lab. Okay, hybrid representations. I don't care as much about this, so we're going to go fast. Basically, the idea is that neural networks are great because they are continuous, and that has a lot of benefits. You can take the derivative of a continuous thing. You can interpolate on a continuous thing. You can zoom in on a continuous thing and get multi-scale representations, which may or may not be accurate. I don't know. But there are reasons to have discrete data structures too. For one, faster data retrieval. I don't know if you all have taken an algorithms class, but all those tree-based structures, super, n log n traversal time, very nice. Here's an example of a bounding volume hierarchy where we have a bunch of squares and you just figure out, okay, did I hit a square? Okay, then what's in the square? Now I'll check those. So you don't have to check everything. It can be a more efficient representation, which means that you can represent more complicated situations or broader situations. I think there's a block nurse paper that tries to represent this huge geographic area in Los Angeles, I believe it is, by basically using one of these or using a similar kind of approach to this. And basically using a NERF on multiple blocks, city blocks, and merging them together. And a single neural network wouldn't be able to do the whole thing. But because they broke it up, they could do it. It's good for sparsity. If you have a lot of states where nothing's happening, that works really well. A discrete data structure that's super good at that kind of thing. And it plugs really nicely into discrete algorithms. Please admire my finite element method M over here. That kind of assume that you're dealing with piecewise, discrete piecewise linear or piecewise polynomial functions. So they talk a little bit about how you could do this. They don't go into too much detail. I'd recommend reading the papers that they link if you're interested in this. But they talk about network tiling and embedding. But it's nice if you have a really sprawling problem with a lot of sparsity or a lot of regularity and you want to plug it into something that assumes that you're using a discrete representation. Cool. So with that, we got that brings us through most of this left hand side over here, the stuff that isn't colorful. We learned that a neural field takes in a spatial input and then output some kind of value. It's a coordinate-based neural network. And we learned a little bit about how we could condition it on more complicated environment, on some kind of latent vector to represent more complicated environments, such as the weather or the time of day or the camera intrinsics, as well as do hybrid representations. So from here, we're going to talk a little bit about the signal and the reconstruction domains, which gets into inverse problems, which is an area that I'm very excited about, because it basically means solving the harder problem, which is always fun. And then we can get into differentiable forward maps. Oh, sorry, that is the inverse problem section. Then we can get into how to actually, manipulate these things. Which is, after all, why we're doing all this. So first of all, let's lay down some vocabulary with forward maps. Who here has heard of forward and inverse problems?
Yes, I did in math and engineering.
Yeah.
Altogether.
Yes, it's a big deal, right? You want to try to define it? I don't want to put you on the spot, but
I'd prefer not to.
cool. All right.
Decade plus of time.
Sorry about that. Cool. Garrett, do you want to give it a try, or should I just give my definition?
I mean, inverse problem.
Yeah.
Basically, you have a bunch of data. You try to reconstruct what the data look like, what the representation of the data. That's how I see the inverse problem. The big inverse problem people do is image denoising problem. A lot of people doing that because it's really nice and very good data problem to solve. Forward problem is you have an equations and you try to use that equations to map that to some domain, from the mapping equations. So that's how I know about kind of forward problem. But inverse problem is harder to solve than forward problem because you don't have the equations. You can estimate or reconstruct the equation basically from the data.
Yeah, so for your example of image denoising, then the forward problem would be taking a perfectly good image and adding noise to it.
Yeah.
Which is actually kind of how these diffusion networks work.
Yeah.
And the inverse problem is then taking a noisy image and then turning it into a much nicer denoised image.
Yeah.
Which is harder than just dumping some noise on a thing. So yes, exactly. And I feel like the definition is a little unfair because kind of like how I think we talked before about how stiff ODEs are defined. I mean, there are different definitions for stiff functions, but really the definition of a stiff function is one that's really annoying to solve with an ODE solver. Similarly here, I think the inverse problem, you can define the problem both ways very often. The inverse problem is a harder one. Which is a bit of a circular definition, but I like it anyway. So here, this is pretty much what Garrett said. A forward problem says that given a complete model, a model might be a set of differential equations. It might be let's take the case here of volumetric rendering. You have, I guess volumetric rendering. Missed Andrew's last message. Which means that you have a 3D representation of your scene, in this case, a big voxel block thing of densities, as well as the color of everything. You have your rendering equation, You have your scene and you have information about your viewing direction. So like, where is your eye and, you know, what's your focal length? And your goal is to find the output of your model. So given a model, find the output of the model. For this example, it's a rendered image from the direction you're looking. The inverse problem is a little harder. Given some observations of a model, of an unknown model, for example, here, a bunch of snapshots from different directions, find the model. So instead of going from model to data, we're going from data to model. And it tends to be sparse, it tends to be an ill-posed problem, which means we don't have enough information to solve it. And that makes it way more fun, right? So they talk a little bit about reconstruction and sensor domains in the paper. They have this lovely diagram here. Basically, the idea is that the reconstruction domain is reality, whatever that is. It is how we represent the actual world. So it might be a mesh, for example. It might be a set of differential equations or parameters for those differential equations. It might be, you know, the position of the eye. I don't know, whatever you want. It's basically the real stuff, the stuff we care about. The sensor domain, on the other hand, is how we understand, how we observe the world. So that might be like a voltage signal you get from a microphone, or it might be a, you know, a snapshot, you know, this nice 256 by 256 grid of numbers that we call an image. And sometimes the reconstruction and the sensor domain are the same. Usually they are not. So for example, here, you see the word SDF a lot in this paper. SDF is a sign distance function. It's a volumetric representation where basically it's a functional way of representing a volume. So it's a function that is defined to be 0 on the boundary. And then other than that, it's the distance to the boundary. So like this little point inside here, 1 unit inside would be a -1. This point over here would be a +1. This point on the boundary would be a 0. Not actually sure where the boundary is. That's what an SDF is. So the reconstruction domain might be the SDF because that's the geometry. And then the sensor domain might be these normal and depth images, which is something that folks use in 3D graphics. Or the sensor domain might be a radiance field, which is color and density fields. And the sensor domain is a bunch of snapshots. And in order to get from the reconstruction to the sensor domain, or from the model to the data, typically you have a forward map. That might be a set of differential equations. That's usually what it is in my field. It might be a volume rendering. I guess also set of differential, or also a differential equation. Or rather integral statement, sorry. Integral equation, which is how you go from a 3D model to, you know, a beautiful rendered image. Or one way to go from a 3D model to a beautiful rendered image. It could be like some kind of meshing algorithm. It could be a Fourier transform. It could be many things. But basically you've got this known forward map to get you from your reconstruction to your sensor. The question then is, how do you get from your sensor domain to your reconstruction domain? So this is a little bit jumpy because this section didn't answer that question. Instead, it talked about a couple of specific examples, specifically PINs, physics-informed neural networks, as well as identity mapping. So there are a couple kind of disjointed slides here. Who here, I think it's been a while since I've talked about physics-informed neural networks. Who here has heard that term before? Sounds familiar?
What was the first word?
Physics-informed neural networks. Cool. Well, if any of you want a really exciting thing to read about on the Metro, that'll make you look smart. Physics-informed neural networks are really cool. Basically, you know how normal neural networks, you have you kind of have input-output pairs. You have your input, and then you have your desired output. You run your input through the network, you get a thing, and then you compare it against your desired output. That's often like your mean squared error loss or your accuracy loss or photometric loss, depending on what problems you're actually trying to solve. And it's a really great strategy if you have a lot of data. Like you need those input-output pairs, you need them to be labeled. And if you have that, then great, that's awesome. You end up with something that Karniadakis calls an observational bias of your network, and it tends to be quite accurate. Very often that's not the case. I work in computational physics, and a lot of our data is trying to get simulation data is super slow, and also it's kind of wrong because we're using all these reduced order models. Trying to get experimental data means that we are trying to waterproof a bunch of things and, you know, setting things on fire and strapping down jet turbines and all sorts of nonsense. And when you're trying to get into like really complicated domains, like the buzzword of not just my lab, but we had a whole class on this in my science policy class, hypersonics, there's like no data there. You have like 3 pictures and good luck. Develop a model, please. Very often you don't have that labeled data. So what do you do then? And physics-informed neural networks are a really cool solution to that. People have been doing physics for a couple years now. We have a few models, and it would be really nice if we could use them. So the idea of physics-informed neural networks is that you take the governing equations. So in this first example, it's the Econial the Econial equations, which a signed distance function needs to obey. Basically, it's saying that the gradient of the sum of the gradient of the parameters needs to be 1. And I forget why that's true. Do you remember? Do you know anything about
No,
this?
definitely well above my pay grade here.
Cool. Well, I'm assuming that somebody somewhere knows what's going on here. But it does, basically, this is required in order for an SDF to be valid. So what you do is you dump it as an extra term on your loss function. You put some kind of weight on it, some kind of Lagrange basically loss weight parameter to make sure that it's well balanced with your error portion of your loss. And then through your stochastic gradient descent, which is basically your drunk guy wandering down a hill in a stochastic manner, trying to find a good local minimum. This is part of it. And it means that not only are you checking for accuracy, but you're also checking that your neural network obeys the governing equations of your physical system at every point. Here's another example from the Mazur-Ricey paper from, I believe, 2019, which kind of popularized the idea of physics-informed neural networks. They're trying to create a surrogate model for Berger's equation, which is basically shock formation in this case 1D. So I think here that they have a accuracy term, but they also have this physical consistency term where basically they say, okay, Berger's equation, we have this, this is what Berger's equation is. We have these governing equations in an analytic form. We have it, we can write it down. It's very exciting. So they rewrite it, they kind of combine terms in a way that they can write it as this term F, or F equals 0. And then they add this term to the loss function where they try to send the norm of F to 0. So basically that, and then they sample that at every point of the training process. They take a whole bunch of collocation points. So they check for accuracy, and then separately they sample a whole bunch of points on their neural network landscape. Run this thing, basically asking the question, does this obey the governing equations of my system? And then uses that as basically an auxiliary signal in order to train the neural network. So it's a really cool way of making sure that your neural networks have some kind of physical consistency. They're not just making stuff up, and they're not just kind of memorizing your data set. They're learning your governing system. That's important in physics. That was
One quick
more.
question, Lee. Is it similar to like the auxiliary task learning kind of problem in this case? because he do both the inverse and inverse problem and forward problem at the same time. So the forward problem is more like the auxiliary task to make sure the inverse problem was solved correctly. That's how I understand it, but you can correct me if I'm wrong.
Maybe I'm having a little bit of trouble understanding you today. I think the connection's a little bad.
Okay.
It sounds like you're, I'm sorry, can you reword that?
Yeah. So do you think like they do the forward mapping and the inverse problem solving together? Are they, so is the forward mapping is an auxiliary task learning problem?
I'm not familiar with the term auxiliary path learning.
So basically, like forward mapping, like ensure the inverse problem, so the inverse problem correctly, the solution become correctly. Is that's how I see it?
Sure. In this paper, actually, this PINS paper from Ricey, they actually have two parts to the paper. I stole this from part one, which is just forward models. Basically, their goal here is to create a surrogate model based on a known system, and that's all they're doing. We've got a couple of different ways of doing that. This one is the most popular because I think it really appeals to the engineers to just dump the PDE into the loss function and call it a day. They're like, yes, that's what I want in my loss function. That's my objective. I would like that to be my objective. It turns out that there are some like practical concerns with this sort of approach. It doesn't train super well. Then they have another one that's entirely self-supervised, which is really cool.
Okay.
But then they have a part two to the paper that is talking about inverse problems and parameter reconstruction. They use a similar set of techniques. They're a little bit different. I don't think they use the term auxiliary learning, but it might be it might be a similar idea, and I definitely recommend checking out the paper if this is in line with your interest. Was that helpful at all?
Yes, it does. Thank you.
Otherwise, I'm not sure if you're still coming out in a couple weeks, but we can talk about it later too, because
Yeah. Okay.
I love talking about this kind of stuff. I'm a normal person with normal hobbies.
Why we're all here. Why we're all here.
That's why we're all here, yeah.
People with normal hobbies.
Yes, we're all normal people with normal hobbies. Learning it's so much stuff and it's so cool. There's so much, but
Yep.
very stressful. I wonder if I'll ever get a PhD. So that's physics informed neural network. Super cool technique. I think a lot of it is focused on forward modeling. Identities is another cool technique. I won't dwell on it, but basically the idea is usually your sensor and your reconstruction domain are different. Like your reconstruction domain is a 3D mesh or a scene. Your sensor domain is a bunch of pictures. Sometimes they're the same. And what does that mean? Does anybody have any ideas of what that means? Like, what are you trying to do if your reconstruction domain and your sensor domain are the same?
It's a wild guess, but like if you're trying to, I'd imagine like trying to like, maybe if you wanted to enhance detail, you're still taking image data and you're outputting also image data in another example.
You know, like the kind of deep fake type thing where like it's like, here's a video, make it, be whatever, Barack Obama, this song,
I didn't even think of that. Yeah, I guess it could be some general autoencoder approach, right? Yeah, that's a really good point. What I had in my head was compression, which is more boring than what you suggested. But this paper, Acorn, which stands for something, and I don't remember what it is, came out in 2020, and basically these folks were, in machine learning land, a 3-year-old paper is ancient, right? But basically these folks were, the idea is they trained a neural network on a single image, or in this case, single 3D meshes. And they did very similar to what you described. Took this discrete representation and turned it into a compact continuous function. They have this lovely chart over here that talks about no, don't do that. I guess you just can't see the last column, it's fine. The last column says pruning, in case anyone wants to see it, and then the one that you can only see part of says multi-scale. And only the neural network is multi-scale. Basically, they are just using this neural network technique to turn their representation into a better one, so that they can zoom in, they can interpolate, they can pick the gradients of things. Everyone always wants to pick the gradients of things. Get a better fine scale representation. And if you pre-train it on, like, I don't know, ImageNet or something, you might even be able to hallucinate some reasonable low-level features, which could be cool. So people do this too. Yes, so I know we are at the 7:30 mark, but Andrew mentioned he specifically wanted to talk about neural networks. So I'm going to have that be the last thing we talk about, okay? Very often these networks use very, very simple MLP type architectures. So if I go back to, I probably should have included that in this slide. If I go back to the NERF in the wild architecture, this is pretty similar to the NERF architecture as well, with the addition of these extra embeddings and an extra MLP here. But basically these are a fairly small, densely connected neural networks. They aren't convolutional neural networks. There's parameter sharing. There's really nothing fancy going on. Basically, you just dump in a 3D position and then it outputs what you want. But it turns out if that's all you do, it doesn't actually train that well. And I think one of the biggest issues for training these things, particularly on image data, but I see this a lot with one of my projects has to do with chemical combustion and basically reacting flow simulations. And you have a lot of time scales in that kind of, in both image data and that kind of problem. Basically, there are areas where not much is going on. And then all of a sudden, a whole lot's going on. You have low frequency and high frequency areas. And one known bias of neural network, of multi-layer perceptrons, trained with STD, is that they're much better at capturing low frequency information, like large smooth regions, than a whole bunch of stuff happening all at once. They're not great at high frequency data. And you know, this property is called spectral bias. I guess, have you all encountered that in your work before? Maybe there's a question mostly for Andrew.
Hey there, this is Andrew. Could you repeat the question?
Oh, sorry, I didn't mean to put you on the spot. I'm curious if you've encountered spectral bias in your work before, basically MLPs that aren't very good at capturing details.
I've encountered more just data set bias. So more from I guess more in the a computer vision domain, that if you train a model to detect cars and then you try to detect a car that it hasn't seen before, that if it's trained well to generalize, it should pick up on the invariant features. But usually in the case, if the new class is really like out of the distribution or from the training like data set, then I could see that maybe that's like a high frequency, or at least from the computer vision, like an intro to computer vision class, how like high frequency in an image would be like color and like texture, and low frequency would be like more like structure, like shape, also contour.
Yeah, that makes a lot of sense. And it actually reminds me of, I do have a little bit of computer vision experience on a project a few years ago. I think not only is it hard to capture high frequency information, it's hard to capture multiple frequencies. I was doing a structure for motion project where we were feeding in basically street view snapshots. My advisor made me ride around with a really stupid looking bike helmet with a 360-degree camera on top. And people kept looking when they thought I couldn't see them, but I saw them in the video later. And we were trying to create depth maps from this. And we had a really hard time. It was almost impossible to capture both the trees and also not put giant void holes in the ground. For the ground in front of us, because either we were capturing that higher frequency or that lower frequency information. You could tune it to do one or the other, but capturing both, super hard. So that is a huge issue in training these things. I think when you get to CNNs, they tend to be a little bit better at this. Because basically you're decomposing the domain into little patches where you look for features as opposed to dealing with all of it all at once. And I believe transformers have a really good way of dealing with this that I think NERF then took and named something else, and they've just been taking off in all kinds of different areas of research. And those are called positional encoding, or otherwise known as high frequency embedding. I think we talked about that a little bit a month ago, right?
Yeah, that seems familiar.
Basically, it is transforming your input by a series of sine and cosine waves of increasingly higher frequencies. So you can see here, we've got, the lower frequency one, which has nice smooth features, changing the input a little bit, only changes the output a little bit. And then we've got high frequency features where changing the input a little bit changes the output a lot. And you can kind of tune how many, what's your maximum frequency gonna be.
Oh,
But what this projection does, what these encodings or projections or embeddings or whatever you want to call them do is, instead of the neural network having to figure out, okay, it's going slow over here and fast over here, it lets you explicitly say, okay, here's the slow stuff, here's the slightly faster stuff, here's the slightly faster stuff, and here's the real fast stuff. As first level, top level features. Neural networks aren't super good at Fourier transforms by themselves, or with the standard, I guess, activation function. And this just makes it much easier to learn both that low frequency and high frequency information. And I've started doing this on like all my projects. It kind of feels like cheating. So yes, Andrew, you want to know what the neural networks are doing? They're doing this. It's a step before your MLP or whatever you're doing. But it's super effective in places where it's needed.
You need information. Do you have to identify the bits that are high frequency and low frequency, or do you just literally just modulate your inputs by that and send them in multiple times?
There is one hyperparameter you need to tune, and that is the maximum frequency you're going to look at. That's it. It's really it really feels like cheating. And the downside is then if you're projecting to a higher dimensional space, that means that you have more dimensions, which means you have more numbers, which means the matrices are bigger. So it's more expensive. It makes your neural network more expensive. But I have found it to be worth it. It's kind of like these are also called Fourier features. It's kind of like a four-man Fourier transform, but with neural networks. Another thing, actually, before moving on, any comments or discussion here?
So you're literally just applying a sine curve to your input data. Nothing fancy in that.
Well, you're applying several.
Yeah, but then
Yeah.
applying several different sine curves and just sending it in multiple times with once this sine curve, once this sine curve.
Yeah.
This sine curve.
And if you're interested in actually trying this out, I think the paper's explanation in NERF is quite good if you stare at it long enough. Or there are so many implementations of NERF in whatever your language of choice is. Field or high frequency embeddings. I think they have a dedicated function for that, and you can just like copy paste and try it out in your own code. So it's nice. Related to that though, it related to the idea of Fourier features. The whole idea of Fourier transforms is adding a bunch of sine waves and cosine waves of frequencies together in order to represent whatever you want. Folks got to thinking, why don't we use periodic activation functions? Why don't we basically, if you have that with a single layer neural network, that is a Fourier transform, like a truncated Fourier transform. If you do that with a multi-layer neural network, that is like a weird nonlinear Fourier transform. That sounds fun. We like Fourier transforms. The reason we don't do that is if you bring up your college calculus, the derivative of a sine or cosine wave is a sine or a cosine wave, which means your loss landscape is like, woo, which isn't great for minimizing. So when you're doing stochastic gradient descent, people don't like periodic activation functions because it just doesn't make sense. But there is this really cool paper that came out in 2020, I believe, called Siren, which is very hard to read because the authors are too smart for their own good. But I think there have been explainers that came out later. I spent a long time with this paper trying to understand it. But basically they are able to, if they're not trying to generalize, create a general surrogate model, but rather like overfit to an image, come up with this compact representation for a single scene or a single thing. They don't need to train. They can actually analytically compute the weights of their periodic neural network and basically get a fancy nonlinear Fourier transform that's really good at capturing high frequency information. Siren was very influential in, I guess, NERF's development. It uses a lot of the same ideas and came beforehand, but it's a really cool thing. I recommend checking it out if you haven't looked at it yet, and then you'll get a headache, and I'm sorry about that, but I suffered, so you have to suffer too. So that's spectral bias, huge issue, but they came up with some really cool tools to solve it. I think number one is much more practical than number two. The second thing here, practicality, is integration and derivatives. So I'll be pretty quick here because it's not quite as relevant, but basically when you're dealing with these networks, for example, these physics informed neural networks, where you're actually putting the PDEs into your loss function. So you have this U sub TT or U sub XX that takes a second derivative of your function with respect to X. It adds an additional constraint to your network and by extension to your activation functions. And that is, it needs to be twice differentiable with respect to X. Otherwise, you're going to have some garbage results. You know, the whole thing about machine learning is we're always taking the derivatives of everything. So that means that ReLU, for example, might not be a good choice for activation function. Instead, you might want to use something like Siren, where that's why they're using sine and cosine waves. It's very, very easy to calculate the derivative. The first derivative, second derivative, nth derivative. It's just another sine or cosine wave. But also things like tan H or sigmoid are, you know, infinitely differentiable. So you need to have those considerations if you're going to use one of these approaches that requires higher order derivatives. Similarly, sometimes you need to take the integral or the antiderivatives, and very often I've seen that put into like a Monte Carlo simulator where you're solving something by, it's like trying to find the area of a circle by throwing a bunch of darts at a circle, counting how many darts they get in the middle. You don't need to do anything there, but if you need to take the antiderivative, a really common strategy is to actually parameterize the antiderivative with your neural network and then take, you know, the n+1 derivative for your actual loss. So not, again, I don't want to dwell on this, but considerations if you need different derivatives or integrals. It's easier to take derivatives than integrals, so try to take more of those and also make sure you can. And one thing I didn't put in here because it wasn't in the paper, but I think it's important, is when you're dealing with these sorts of physics-based simulations, which you often are when you're trying to parameterize a field, sampling is a huge issue. And this paper doesn't talk about it, but I think the NERF paper actually did a very clever thing here, where they jointly trained two networks, a coarse and a fine network. And one was to try to estimate the probability distribution of like, where is stuff happening? And then the second took finer samples in that area and actually tried to figure out the density and the color. So I'm currently trying to steal that approach for one of my codes, and we'll see how well it works in other domains. But sampling is a huge issue in these sorts of things because very often you don't care about all space equally. Cool. All right, I'm going to just end there. But we can have further discussion if you want, because I believe we've,
Yeah, we've compressed the time frame a bit, but yeah, I think we can talk for at least a few minutes. We've got a question.
sure, any questions, comments, concerns, or ponderings on neural fields?
The editing stuff sounds interesting. I'm gonna look at that, like, yeah, rather than.
The stuff right after where we got it.
Or
I'm sorry.
okay. Yeah, like rather than trying to like manipulate the input to get the desired output, just train it and then.
Yeah, and in computer vision, they're getting very clever about figuring out ways to get from A to B, right? We I think, I forget what the name of the paper was. There was something in my computer graphics class we were discussing. First it used pretty aggressive latent variables. The idea was based on a person standing there, a few pictures of a person. Bye Garrett, good to see you.
Thanks, coming.
Based on a few pictures of a person, they tried to make they succeeded to make an avatar of this person and then make him dance in various ways. Which I guess is a common research problem because it's hilarious. So they had this really complicated, I think it was called Simple actually, skinned multi. I forget. Anyway, they have this avatar model that basically embeds how avatars work with some extra person specific appearance embeddings. And then, sorry, where I was going with that was they did some really interesting stuff with then once they have this avatar model, how do you edit it in useful ways? How do you manipulate it to make it dance and like move around in ways that are realistic? Like how do you make the fat shift and how do you? Pretty cool.
Yeah, sure. Yeah, that's another thing that's interesting to me. Like, yeah, all this stuff tends to focus on like static models, but like, yeah, when you have like what about like skin models, like when you're actually.
Yeah.
So, yeah.
And learning from video too.
Yeah. There's like
your
the
scenes deforming.
yeah. The problem that's like, okay, we're just going to generate that skeleton, which is kind of a solved problem now. But then the actual like, what if you want to basically a 4D nerf where it's like moving? I think that's not a solved problem yet, but it's kind of interesting.
That was really interesting that you might be familiar with this piece. Hang on, I'm going to bring up my computer vision lecture real quick. We've got the paper in it. It was nerd-based avatar. I'm not going to share this on a recorded thing because they're not my slides. Yeah, use simple thing. One thing that was really cool about this paper, which was called, what was it called? Wow, apparently we did a lot of stuff on this paper. Sorry, it was called, I think it was Neural Actor, or possibly hybrid volumetric textural rendering for human avatars. Or possibly many more. They said that they tried to use some more complicated like skin skeleton models, but they found that this simple model actually did better than anything else. I think they were figuring, or they were kind of speculating on why this simple like skeleton-based model is better than the stuff that's supposed to do better, with polynomials and all that in it. And they were speculating that since you're learning a correction anyway in this kind of approach, it's easier to learn from a more linear, predictable base. then it's kind of unpredictable polynomial things. But the results were not what I was expecting.
It was cool.
Oh, cool collab. Thanks, Andrew. Andrew just posted a cool collab where you can see Siren and play around with it. Yeah, nice. That's really helpful because I feel like there's a
Um,
lot of math in the paper, so having something tangible to mess around with would be really helpful there.
So a question that I have is that, so with the encoding, because you could just, right, so you could send the raw, I guess, for nerf, it's the, I guess, all of the information for the camera to then generate the RGB, but with like, I guess like with Siren, you're encoding the frequency. And so then the MLP is learning, like, what is it learning? If
Oh.
if you have an idea. Yeah, because it's
Yeah.
hard for me to conceptualize.
So I think it's that's conflating two things a little bit. I think Siren it inspired Nerf in many ways, or it used techniques that helped Nerf along. But I don't believe Nerf used Siren's techniques directly. So they use positional encodings instead of periodic activation functions. So Siren, it was basically what you're learning is Fourier parameters or Fourier coefficients, basically. So with Siren, the activation functions are periodic, and therefore you're taking a linear combination of sines and cosines at different frequencies with a non-linearity in between. At least in my head, it's just a fancy Fourier transform, where they were able to derive a closed form way of setting the weights in that network, so you don't have to actually try to train on this horrible periodic landscape. Bye, Micah. It was great to digitally see you.
Right, see you in a bit.
Bye. Thanks so much. That was great. Okay. Bye, everyone.
All right.
In Nerf, how positional encodings are used, I think they're just a projection of your input, and then the MLP is all the parameters afterwards. So you, instead of having, you could have X and Y, and then you have, a matrix multiplication with tan H and matrix multiplication with tan H, and then you have some divided output. Instead of doing that, you have like sine X, sine Y, sine 2X, sine 2Y, sine 3X, sine 3Y. I forget how exactly they do it. Definitely not that. But basically you just have a much larger feature space. But then the actual MLP parameters are the same. So it, yes, I lost my train of thought. Did that help at all, or
Yeah.
get close?
Yeah, it helps, I guess. Yeah, it's just really interesting. It's like, what can neural networks not do, right?
Yeah. Mhm.
And but yeah, it's interesting to think how you don't have to, because like with neural networks, people just usually try to like have the network generate its own like representation. But I think for the Siren and using like trying to estimate the Fourier like coefficients, I think there was something where like MLPs struggle with, right? Like high frequency like information, to like reconstruct a signal. So that's cool that someone from a signal processing background is like, oh, let's make the problem easier, and actually does better. So that's pretty cool.
Someone was willing to go through all that math. Oh my goodness.
So you've got like basically all graphics, this signal processing, like nothing new, like.
I don't know. So I thought grad school would make me more precise about things and have a more concrete idea of what's going on. I don't know what reality is anymore, and I'm pretty sure everything is everything. That's where I am right now. I don't know if it was like that for anyone else, but
No, so with the going back to additional code, there's no like processing you have to do on the output to like, because aren't there going to be like sine waves in the generated output? Because the sine wave is it, but I don't know that like that's not actually a feature, that's just the sine wave that
No.
you put in the.
It's I mean, you're not actually putting in sine waves, so you can kind of see in these little dots here. Basically, your input feature is some value, like you've got a scalar
Yep.
or vector
Yeah,
or whatever.
it's like
And you are running your values through these sine waves. So let's say your value is 4 or whatever this is. 4 is this over here, and then this over a vector that's this and this and this, and the difference or where the frequency comes in is if you have a slight perturbation on your input, which if you think about training over a bunch of input samples, you do have perturbations on your input. This feature doesn't change very much. This feature changes more, this feature changes, you know, you go from the bottom to the top. You have a whole sign change there. So that's where the frequency comes in. So you're not actually passing in a sine wave. You're still just passing in values, but the frequency information is encoded on how it responds to perturbations, I suppose. I don't know if that made it clearer or worse.
yeah, that makes sense, I think.
One thing that might be fun actually for a future meeting, because I feel like one thing we like playing with here is why is the neural network doing the dumb thing it's doing and why isn't it doing the thing I want it to do? Which seems to be a really big research area right now. I wonder if we could do like an interactive thing where we play with positional encodings or the large margin, like the implicit bias of stochastic gradient descent as a large margin maximizer, or the things that neural networks are learning.
Yeah, that'd be down for that.
I also realize that there are whole research areas that are not neural networks, but.
Yeah, we haven't quite ML heavy these last
So what's your computer interest area?
I find a little lack of good literature, but for around, I really enjoy the World Wide Web as like a medium for technology and creativity. And I'm very interested and hopeful that someday we'll have like a little more. One of the things that appeals to the web about me is that I think it is like closer to being a direct user manipulatable system than like many of the alternative computing technologies in the universe, and trying to do something to like bridge the user computer divide and let people interface with computers more honestly is like very high on my moral ethical priority list. So
That's really neat.
like has some like neat droppings there for me, although it is still quite impervious and quite far off.
No, it's fine. Next week you'll just solve the internet.
So yeah, we're open to, and also like the thing I'm personally into is like more kind of foundational stuff, like the original, like I'd say like could we do the original MLP paper, or like could we do the original like World Wide Web paper, the what's his name, with the guy at CERN that did the
Roy Fielding and the rest paper, or Tim Berners-Lee.
Tim Berners-Lee, I think. Well, yeah, Timothy was the one I think of, but like yeah, whichever one you consider foundational, I'm always like that's my personal. I'm always interested in seeing stuff like that.
I love a good systems paper too. Like we've like loved to find something for like Linux kernels like gotten really good asynchronous IO.
Yeah, so my battery's about to die, so I'm rather than plug in my computer, I think it's like time to thank you very much. Yep, really.
Thank you all for coming, and I believe we don't have a speaker for next time.
Yeah, so yeah, we are looking for speakers, so anyone here or online who wants to
The one person online.
yeah,
Everybody can.
yeah.
I'm also happy to like continue the second part of the paper at a future meeting.
So you're the only person here who hasn't spoken yet, so. Not the speaking 2 times is a problem, but.
I can definitely like start looking, but I don't think I'm ready for the next meetup.
Yeah.
Yeah.
Also, if there are papers that you would like covered but don't feel qualified to cover, then
So make suggestions and,
Yeah.
or even just areas like they've been very ML And like I'm mainly like graphics, like 3D graphics, so like ML and.
AI ethics, that's a good idea.
Yeah, oh,
Like,
yeah,
what-
yep, that sounds like a good.
Right, yeah, we were talking about that last meeting.
Yes,
That's
yes.
fascinating.
Yep.
Actually, talking about the World Wide Web, one thing that I've been very interested in lately is like consent in ubiquitous computing. So not just websites, but getting into the IoT stuff, like everything's networked with everything and
Yeah.
computing all the time and knows where you are and you don't have to participate in the
Yeah.
process.
Yeah.
Yeah.
Creepy.
Exactly. Yeah, no.
You don't know anything.
Yeah.
Data.
Yeah.
Oh my goodness.
Yeah.
It always seems like internet things went straight from like your thing is like a black box that does probably have a computer in it, but like you can't really program it.
Yeah.
And it went straight to and it's definitely not connected to the internet. Straight to your thing is a black box, you can't program it, but it's also like selling your private data online. There's
Yes.
never like an intermediate period where it's like, hey, you can now like hack around with your toaster and like see if you like run your code on it. Like
It's like
it kind of skipped
Well,
that.
put on my-
Yeah, like it skipped that step completely. It went from just like dumb to smart without like, hey, let's make it hackable in the middle. I was kind of
It's
disappointed
definitely
with that.
somewhat intermediated still, but I've been super impressed with like the Google Chromecast device, the original ones, like now it's starting to turn more IoT-ish, but like, it's like, this is just like you can like load a web page like remotely and control this web page remotely, is basically all it is.
That's how all our kids watch TV.
It's such a lovely, like, dumb device. It's a
Yep.
dumb, smart device. It's like, I am a blank slate. I don't really do anything.
Yeah.
Yes, love it.
Yeah.
Right, I will.
See you,
Thank everyone, bye everyone.